Assalamualaikum. Let's see 16 PSK. 16 PSK is an M array encoding technique where M is 16. That means there are 16 different output phases possible. So that means we will have a group of 4 bits. Means each symbol will have 4 bits. Means at a time we will be transmitting 4 bits in one signaling element. That is how 16 different output phases possible. With 16 PSK, 4 bits called quad bits are combined, producing 16 different output phases. The minimum bandwidth and baud are equal to 1/4 of the bit range. So 16 PSK truth table and concentration diagram, you can see uh, at all zeros, when 4 bits are all zeros, phase is 11.25 degrees, then 33.75 degrees. Difference of 22.5 degrees there between the consecutive symbols. So with this 16 PSK, the advantage is that we can transmit more bit rate, more number of bits in the less bandwidth. Means uh, if B is the bit rate, then the bandwidth requirement will be FB by 4. That means we can transmit 4 times of the bandwidth we can transmit. You can say that the bit rate of 16 PSK will be 4 times greater than that of the BPSK. But the problem is that the spacing between the symbols is too narrow. So that may cause bit error rate if 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 the channel has any impairments. So as the level of encoding increases, that is the values of N and M increase, more output phases are possible, and the closer each point on the constellation diagram is to an adjacent point. That's the point that I am making, that when we increase M, the output phases will be more closer to each other on the constellation. As we've seen, that may cause the errors. With PSK, 16 PSK, the angular separation between adjacent output phases is only 22.5 degrees. Whereas in BPSK it is 180 degrees. Then we have 90 degrees, then we have 45 degrees. Now we have only 22.5 degrees. Therefore, 16 PSK can undergo only 11.25 degrees phase shift during transmission and still retain its integrity. So for an MRA system with 64 output phases, that is n is equal to 6, the angular separation between adjacent phases is only 5.6 degrees. This is an obvious limitation in the level of encoding possible with PSK, as a point is eventually reached where receivers cannot recognize the phase of the received signaling element. So with PSK, we cannot go infinitely to a large modulation order. So at a point when the angle separation between the neighboring symbols is too small, receivers will not able to understand. So at that point, we cannot achieve this any PSK modulation. So the order of the PSK modulation is limited. Uh, After a certain value, we cannot go with the PSK modulation. In addition, phase impairments inherent of communications lines have a tendency to shift the phase of the PSK signal, so this could destroy its integrity and producing errors. So there are phase impairments. Impairments means factors that affect the power of the signal are tend to that include also intercept interference. So these impairments are inherent on communications. So they have the tendency to shift the phase of the PSK signal. So the modulation of the PSK, the information is in the phase, and if there is a shift in the phase of the PSK signal, that will destroy its integrity and that will cause errors. On the other hand, we have QAM, that is quadrature amplitude modulation. So due to the limitation of 16 PSK, as we've seen with 16 PSK, the difference between the consecutive symbols was only 22.5 degrees. So on either side, it can go up to 11.25 degrees, means a shift of 11.25 degrees is only tolerable with 16 PSK. Uh, if any shift comes greater than 11.25 in 16 PSK, then the receiver will not be able to understand the symbols information because PSK PSK modulate the information in the phases, and if phases shift so much that receiver couldn't understand it, then there is no point of making PSK as a modulation scheme. So with PSK, we have to be very careful in choosing the order of the modulation scheme. So due to this PSK limitations, we have another form of digital modulation that is similar to PSK, except that digital information is contained in both the amplitude and the phase of the transmitted carrier. So as the name suggests, quadrature amplitude modulation, here we keep the information or modulate the information in both in amplitude as well as phase. So when we have amplitude and phase as the information carriers are the characteristics that we want to modulate, then we have more choices with QAM compared to only with PSK. So with QAM, amplitude and phase shifting are combined in such a way that the positions of the signaling elements on the constellation diagrams are optimized to achieve the greatest distance between elements, that reducing the likelihood of one element being misinterpreted as another element. So that is the aim behind the QAM. We want to optimize the distance between the neighboring cells, between the neighboring symbols, so that will reduce the likelihood of error, that one element may be misinterpreted with the another element, or the shift is not that too much that it goes into the area of the another element. So this reduces the likelihood of errors occurring. So first, let's see HQM transmitter. That is an AIM array encoding technique where AIM is equal to 8. Unlike 8 PSK, the output signal from an 8QM modulator is not constant amplitude signal. Now, as we are modulating amplitude as well as phase, so QAM cannot be said as a constant amplitude modulating signal. It's a non-constant because we are also modulating amplitude for the information. So it's different from the 8 PSK. Figure 30A shows the block diagram of an 8QAM transmitter. Let's see the figure. So that is the 8QAM transmitter where you can see its block diagram, truth table, and 4-level converter. So 8QAM, that means 2 power 3. That means 3 bits at a time. So we have now 3 channels: Q, quadrature channel; I, in phase channel; C, control channel. So I channel will be as it is, and it will be converted in the first step. It will be converted from 2 to 4 level converter because C will be there. So if I is equal to 0 and C is also equal to 0, then it will be given as output minus 0.541, and that will be multiplied with sine omega ct. On the other side, if Q is also 0, C is 0, then again it is minus 0.541. But that will be multiplied with the quadrature component of the sine omega ct, that is cos omega ct. Then those will be summed in linear summer passed through the band pass filter, and at the output we will get plus minus sine omega ct and plus minus cos omega ct multiplied with any of these voltage levels, either minus 0.541, minus 1.307. So that it will be the output at the out of this diagram. So as you can see, the only difference between the 8QM transmitter and the 8PSK transmitter shown in figure 23 is the omission of the inverter between the C channel and the Q product modulator. If you go back and see 23 figure, there we will see C channel used an inverter output. Here we don't have any inverter output for the C control channel. As with 8PSK, the incoming data are divided into groups of 3 bits. The I, Q, and C bit is each with a bit rate equal to 1/3 of the incoming data rate. So that is very true. That is also shown in the figure. You can see the input bit rate is f of b divided by into 3 f b of 3. So the 3 channels have the data rate equal to fb by 3. Again, the I and Q bits determine the polarity of the PAM signal at the output of the 2 to 4 level converters, and the C channel determines the magnitude because the C bit is fed uninverted to both the I and Q channel. The magnitudes of the I and Q PAM signals are always equal. Their polarities depend on the logic condition of the I and Q bits and therefore may be different. So that is another advantage of this 8QM, that the magnitude of these two will be same because I and Q are the same. When I and Q is 0, it is minus 0.541. When they are 1, it is plus 0.541. And you can see the magnitude is from here. When 0, we have magnitude of 0.541. When 0, again, we have 0.541. When it is 1, it is 1.307. Only the polarity is determined by the I and Q. When both are 0, then the polarity is 0. When both are 1, polarity is positive. So the output will be plus minus 0.541 sine omega ct and plus minus cos omega ct, or plus minus 1.307 sine omega ct plus minus cos 1.307 cos omega ct. So example is given here to further elaborate the diagram for a tri-bit input of Q is equal to 0, I is 0, and C is equal to 0. Determine the output amplitude and phase for the 8QM transmitter shown in figure 38. So the inputs to the I channel 2 to 4 level converter are 0, 0. So that means it will choose, means it will output will be minus 0.541 sine omega ct minus 0.541 cos omega ct. So I channel output will be this. Q channel, when you combine, the output will be this one, 0.541 sine omega ct minus 0.541 cos omega ct. When you further solve this one, it will be like 0.765 sine omega ct minus 135 degrees. So for the remaining try bits, I suggest you to at least do 1 or 2 examples. You know that how to solve from there to here. Yesterday we did that. Uh, Using the sine alpha and sine beta quantities, you can solve this one. First, you take the minus 0.541 common, and then you will manipulate the sine omega ct and cos omega ct accordingly to find this 0.765 and sine omega ct 135. So 8QM modulator, truth table, this one. When we have binary input the 000, the output amplitude will be 0.765 and angle will be minus 135. Now you can see this is the phasor diagram and this is the constellation diagram. See on one angle that is 45, this is 45. We have two amplitudes. One is here and one is here. So that is two information, or you can say the 6 bits are transmitted on each phase. So if you had the 8 PSK, in that we will be having the 8 phases here, but we have only 4 phases. So with QM, we able to reduce the number of phases required if we had the 8 PSK. Bandwidth consideration, we already talked about that. The bandwidth required for 8QM is FB/3, the same as in 8 PSK. Then figure 28 shows the 8QM receiver, where we have band pass filter, Powell's filter. The input will be plus minus 0.541 sin omega ct plus minus 0.541 cos omega ct or plus minus 1.3 something sin omega ct plus minus something cos omega ct. So that will be the input at here. That will be splitted into two channels, I channel and Q channel, and the state will be carrier recovery. That will be multiplied with the product detector, that is sin omega ct and cos omega ct. Then we have the 4-level PAM converter that will convert 4-level into I and C dash and Q. There will go and we will take only QIC as the output, and again we will have the clock recovery. So an HQM receiver is almost identical to the 8PSK receiver shown in figure 28. The differences are the PAM levels at the output of the product detector and the binary signals at the output of the A to D converters, because there are two transmit amplitudes possible with 8QM that are different from those achievable with 8PSK. The four gene modulated PAM levels in HQM are different from those in 8PSK. Therefore, the conversion factor for the A to D converter must also be different. Also with 8QM, the binary output signals from the I channel analog to digital converter are the I and C bits, and the binary output signals from the Q channel A to D converter are the Q and C bits. So to solve this 8QM receiver, you must go to 8PSK receiver in figure 28, because the two diagrams are same, the two receivers are the same, but you can also solve this by looking at the diagram and providing some input here and solving it uh, with this 4-level PAM converter that was same that we have seen in the transmitter side. So this one, but that will be in the reverse direction. Then we have 8QM 16QM transmitter as with the 16 PSK. 16QM is an M array system where M is equal to 16. The input data are acted on in groups of 4. So we seen 16 PSK. The problem was with 16 PSK is that the angle difference between the neighboring symbols was too small. So let's see whether 16QM is in phase, whether it is robust. uh, against 16 PSK or not. So the input data are acted on groups of 4 as with 8QM. Both the phase and amplitude of the transmit carrier are varied. The block diagram for 16QM transmitter is shown in figure double three. So that is here figure double three, where you can see we have now 4 channels Q, Q dash, I dash. So the input binary input data rate is FB, that will be divided into FB by 4. So each channel will have a data rate of FB by 4. That will go to 2 to 4 level converter. Now we have two tables I dash and Q dash. So if two are 0, I dash, then the output voltage will be 0.22 multiplied with the wellness modulator sin omega ct in case of I channel and cos omega ct in the case of Q channel. Then both will be summed here and the output will pass through band pass filter and we will have one of the outputs as the 16 QM. So the outputs can be uh, minus 0.22 sin omega ct plus minus 0.22 cos omega ct or plus minus 0.821 sin omega ct plus minus 821 cos omega ct or plus minus 0.22 sin omega ct plus minus 0.821 cos omega ct plus minus 0.821 sin omega ct plus minus 0.821 cos omega ct. So these will be the 16 outputs from the 16 QAM modulator. So for a quad bit, 4 outputs, 4 zeros. In case of 4 zeros, the our I output will be minus 0.22 sin omega ct, and Q output will be minus 0.22 cos omega ct. So when we sum them, it will be minus 0.22 sin omega ct and minus 0.22 cos omega ct. That is one output, and that will be drawn at amplitude 0.311 and angle is 135. So here it's a list where you can see the binary input, their respective amplitude and their respective angle is shown. And the diagram can be like this one. This is the phasor diagram. This is the constellation diagram. You can see on one phase we have these 8 bits. On this phase we have 4 bits, and on this phase we have 4 bits. So the separation between the two phases is like 30, 30 degrees between the two. So this one is 45 and this is 15 and this one is 75. This one is 75. So with 16 PSK, the angle separation was 22.5, and with 16 QM, the angle separation is 30 degrees. So 16 QM has a better will have a better bit error rate compared to 16 PSK. A bandwidth will be same, will be needed FB by 4 bandwidths. That means for the same given bandwidth, we can transmit 4 times more bit rate using 16 QM compared to BPSK. Uh, that's it from this lecture. If you have any questions from this one, you can ask. So bandwidth considerations of 16 QM with 16 QM as the input data are divided into four channels. The bitrate in the I dash Q or Q dash channel is equal to 1/4 of the binary input data rate. So that we can see or verify from the diagram as well. The bit splitter stretches the I dash Q and Q dash bits to four times their input bit length, also because the I dash Q and Q dash bits are outputted simultaneously and in parallel. The 2 to 4 level converters see a change in their inputs and outputs at a rate equal to 1/4 of the input data rate. So the job of bit is filtered to make I dash Q and Q dash slower because the actual bit rate is f of b. So if we transmit these with the actual bit rate, then they will not be uh, added properly. So we make them slower by changing or stretching them to the length of 4 bits rather than 1 bit. So the data rate will become FB by 4. So figure 36 shows the bit timing relationship between the binary input data, the I dash Q and Q dash channel data, and the PAM signal. Figure 36. So this one is the figure 36. You can see the actual input bit is 1010. The I dash channel become FB by 4. That means it takes 4 bits now to be transmitted. Similarly, I channel, similarly, Q and Q dash channel will also be. This is I channel PAM output on 4 different voltages. And this is I channel balance modulator output, that is minus 0.821 sine omega CT, then plus 0.22 sine omega CT, and again minus 0.22 sine omega CT. So this FB become FB by 4. That means stretching the all channels up to 4 times of the bit time or the bit of the actual input data. Then we have the balance modulator, and the output is that we can see in the uh, below figure. It can be seen the highest fundamental frequency in these channels is equal to 1/8 of the bit rate of the binary input data. Only cycle in the I dash channel takes the same amount of time as the 8 input bits. Also, the highest fundamental frequency of either PAM signal is equal to 1/8 of the binary input bit rate. So the bandwidth will be always 1 divided by 2, half of to that of the bit rate. So bit rate is FB by 4. So the bandwidth will be FB by 8. That will be 1/8 of the bit rate. So with a 16 QM modulator, there is no one change in the output signal for every 4 bits, for every 4 input data bits. That's true because that signaling element will change after 4 bits. Consequently, the part will be equal to FB by 4, the same as the minimum bandwidth. So this is how we calculate the bandwidth from the product modulator. Then we have example double one. Find a 16 QM modulator with an input data rate equal to 10 megabits per second and a carrier frequency of this determine the minimum double-sided Nyquist frequency and the bar. Also compare the results with those achieved with BPSK, QPSK, and ATSK modulators. In examples 4, 6, and 8, use the 16 QM block diagram shown in figure double 3 as the modulator model. So let's see this example. The first is we have 16 QM modulator. So for 16 QM modulator, the bit rate will be equal to FB by 4. That will be 2.5 megabits per second. And fundamental frequency will be half uh, of that of the bit rate, that will be 1.25 megahertz. And the bandwidth requirement will be equal to f of b by 4. That means 10 megabits per second by 4, that is 2.5 megahertz. And the baud will be also equal to 2.5 mega baud. For the following modulation scheme, construct a table showing the number of bits encoded, number of output conditions, minimum bandwidth, and baud for an information data rate of 12 kilobits per second. So try to solve this example. I give you like 10 minutes. So in 10 minutes time, you should solve this one. I will see you after 10 minutes. Okay, so only two students have sent the solution. What about others? Only 49 and 20. 192 20 send the solution. Where are others? What about others? So this is the solution. You can see here table will be like this one. Whereas this table summarizes the relation between the number of bits encoded, number of output conditions, minimum bandwidths, and the port for all the modulation schemes, ASK, PSK, FSK, QAM. Then we have bandwidth efficiency, sometimes called information density or spectral density, is often used to compare the performance of one digital modulation technique to another. In a sense, bandwidth efficiency is the ratio of the transmission bit rate to the minimum bandwidth. That means how many bits we can transmit per hertz. एक hertz में कितने bits transmit कर सकते हैं? That is the bandwidth efficiency. Mathematically, it is given as transmission bit rate, bits per second, and minimum bandwidth hertz, that is bits per second. Bits per second are cycles per second. So second will be cancelled. That is bits per cycle. How many bits we can transmit in one cycle? That is your bandwidth efficiency. Or how many bits we can transmit in 1 hertz. That is again the correct. So for an PSK system operating with an information bit rate of 24 kilobits per second, determine baud minimum bandwidth and bandwidth efficiency. So it's 8 PSK, that means 2 power 3. So 24 divided by 3, that is 8 kilohertz. So bandwidth will be 8 kilohertz. Baud will also be equal to 8 kilohertz, 8 kilobaud, and bandwidth efficiency will be 3 bits per second per cycle of bandwidth. Similarly, 16 for a 16 QSK and transmission system with a 10 kilohertz determine the maximum bit rate. So that will be 40,000 bits per second. So that is the table 2 shows the summary of all the modulation schemes, possible output, minimum bandwidth, baud, and bandwidth efficiency. These are some unsolved problems. Try to solve them. Maybe few of these will come in your final exam, final semester exam. Not all, but few. Okay, that's concludes this lecture as well. If you have any questions from this one, you can ask. Okay, see you tomorrow with a new lecture. Have a nice day. Allah Hafiz.